Hello everyone. Um, Today I would like to present my work on first time miss, which is a low overhead defense against shared memory cache side channels. My name is Karthik and I'm a PhD student at the University of Minnesota. It's a pleasure to be here today. Um, so let me start with the outline of the talk. The we start with the security issue, and the security issue is kind of the motivation for why we want to have a first timers approach. And we also look at mitigation approaches which are already existing for this security problem, how our first timers approach is, and then also how it is implemented. And then lastly, we look at the simulation results and then conclude the talk. Okay, so let's look at the security issue first. The main security problem is that there can be information leakage due to extra cache hits, and we can explain what this means using an example. So if you look at the bottom figure, you'll see that there's a cache which initially is empty and doesn't have anything in it, and then there's a victim. You can think of the victim as a process. There's a victim process which installs a cache line into it, so that installed cache line is marked in red. And following that, there's an attacker process. It's also a process, and the attacker process is accessing the same cache line because it was a part of shared memory, and the attacker then would have a low access time because it was in the cache, and therefore it would detect that the cache line was in the cache. And this is a kind of information leakage because the attacker now knows that the victim accessed a particular cache line, and we don't want the attacker to know anything about what the victim is doing. So we'd like to mitigate this security issue. Okay, there are already several existing approaches to deal with such cache side channel attacks, but we look at two popular ones. One of them is called cache partitioning, and the other one is called address set randomization. So let's look at cache partitioning first. So in cache partitioning, the cache resources are split between the users of the cache. And in this case, if you look at the example figure on the left side, we've shown a partition between a victim process and an attacker process for a two-way associative cache with just two sets. So and this is a way partitioning scheme. So in the example, so it's kind of the victim has two sets for itself and the attacker has two sets for itself. And when the victim accesses a cache line, then it installs the cache line into its partition. And then when the attacker accesses the same cache line, so although it's basically the same cache line address, the attacker then gets a separate copy of that cache line in its own partition. And that's because the attacker cannot access any cache line outside its partition. And so this is effective to prevent reuse of shared cache lines, and which is good in terms of security. And then on the right side of the figure, we can look at address set randomization. And address set randomization, the victim now, when it accesses the cache line, it gets put into a random cache location dependent on some randomization function. And then the attacker also will put its cache line into some random location, even though it's the same cache line address. Since the randomization for the attacker is different than the randomization for the victim, therefore the location of the cache line is also different. And the attacker gets its own copy of the cache line. So this is also effective to prevent cache line reuse, and therefore good for security. But both of these approaches are not perfect, and they do have their own drawbacks. So for partitioning, the major drawback is that if you partition the resources, then if a process might require more resources, then it will not be able to get it because it can only access the resources inside its own partition. So that might affect the performance of some processes. And the second problem is that we have duplication of cache lines, which means that the cache resources are less efficiently being used. It would be nicer to just use one cache line or one cache entry for one cache line instead of using the same cache line copied over multiple times. And this duplication issue is also a problem for address set randomization. So, so these approaches, while they're good for security, they also have some drawbacks which we would like to get rid of. And our approach is known as first time miss, and the main thing that we want to achieve is to eliminate the drawbacks of the existing approaches. So we don't want any cache duplication, we don't want any cache line duplication or partitioning, and at the same time we also want the security benefits that those approaches have. And to do that, we use a delay based mechanism. So to explain this mechanism, we can look at the bottom figures example, and you see that the victim accesses the cache line and installs it into the cache, and that's known as the red square. Next, the attacker will access that cache line. It accesses the same cache line, and there's no duplication, but instead of receiving the contents of the cache line immediately, there's a delay, and the attacker needs to wait until that delay is completed. And on the rightmost part of the figure, you see that the delay is completed and the attacker receives the contents of the cache line, but because of this delay, the attacker does not know that the cache line actually came from the cache, and since it might be a long delay, and it might appear that the contents of the cache line actually came in from main memory. So this kind of confuses the attacker, because the timing is no longer reliable for the attacker to determine the position or what it accessed in order to get something or to get some information. So so this is the basic approach, and this approach is nice because it has it has the same cache utilization as a normal cache, but it has some extra security benefits. Alright, so we implemented this approach using we added some new hardware to the cache. So in this figure, we see that on the top part of the figure, there's a fairly standard cache implementation there, but the extra component we added is the FTM buffer, which is the first time miss buffer, and this FTM buffer is between the private cache and the interconnect, and its size is similar to the number of MSHRs in the private cache. And that's because we want to have we want any outstanding access from the private caches to be possibly converted to a first time miss. So we should have enough capacity for that. And if you look at the bottom of the figure, you'll see the buffer entry and L3 entry. So the FTM buffer, or the delay buffer, is it contains one cache line in it, and also contains V and W, which are valid and wait bits, and these two bits are used for implementing the first time miss mechanism, which we will look at coming up. And the L3 entry is essentially the same as a normal L3 entry, but we've just shown it here just because it will be used in the first time miss mechanism. And there's a cache line in there, and there's also sharer bits, and in this case there are 4 sharer bits, which we've shown S1 to S4. So these are the hardware changes that we made. So now let's look at how do we use these hardware changes in order to implement first time miss, our first time miss mechanism. So in this case, you'll notice that there's actually 2 cases. So let's look at the first case, and in this case we look at a cache access to the last level cache, or the L3 cache, and so if you observe in 1A that we have a cache hit in the L3 cache line, meaning that we found the cache line that we want to access, but if you look at the sharer bits of the L3 cache, there is one white bit which means the bit is not set, and there are 3 gray bits which means that they are set, which means there are 3 sharers, and there's one core which is not a sharer, and so we are the core which is not the sharer. So since the sharer bit is not set, we are sure that we've never accessed this cache line before, and if we never accessed this cache line before, then we should not be able to it might be a security issue if we do access it, because if we are the attacker, then we discover that someone else had put the cache line in there. So we should implement, or we should have a first time miss delay to hide the presence of this cache line. And so in order to do that, we go to step 1b, which is the delay step. And in this step, the contents of the cache line are sent to the buffer, and a memory delay request is also sent to main memory. In the buffer, the valid bit is set, saying that that buffer entry is populated, and the wait bit, however, is not yet set, because we are still waiting in order to get a response from main memory. And in the last step, which is the response step, we get a response from main memory, and then we set the wait bit, and at that point the buffer entry can be sent to the private cache. So what we've done is we have delayed the contents of the cache line being sent to the private cache by about the duration of a memory access. So we've kind of confused the attacker to think that it's actually a memory access when it was in fact a cache hit in the last level cache. Okay, so this is one case where so this is one simple case, and then we can also have another case which is which could happen. And in this case, if you look at the access step in 1a, we access the shared cache and there is a cache hit again, but the sharer situation is a little bit different. So there are 3 cores which do not have a copy of the cache line, and there's one core which does have a copy of the cache line, or at least it could have a copy of the cache line because the sharer bit is set. And when this happens, then the coherence protocol requires that we should check the remote private cache in order to see if there is some change to the contents of the cache line which that remote cache would have done but have not been updated in the last level cache, just for efficiency. And that's how the coherence protocols are commonly work. So if we do that, because of that, so we do that. So a forward request is sent to the remote cache, and then in the step 2b, which is the delay step, we get the response back, and at the same time the delay message has already been sent to main memory because we want to simulate a main memory delay, and the response has written will write into the shared cache entry, but will also write into the delay buffer, and then it will also set the sharer bit, as we see, because now we are a sharer of the cache line. And then in step 2c, which is a response step, we will get a response from main memory, and at that point it will set the wait bit of that valid of the buffer entry, of the delay buffer entry, and then the delay buffer will send the contents to the main cache. So we will still have an access time to the cache line similar to a main memory delay. So this is still going to confuse the attacker, and the attacker won't be able to tell, or it will be very hard to tell that the access actually came from this kind of obfuscated mechanism, and it will actually look like it came from a memory access. Okay, so let's go to so now that we've seen the mechanism, we implemented it on a architecture simulator. So let's look at some of the results that we got once we simulated this mechanism. So we implemented first time miss without any other protections or any other cache side channel protections, and we also implemented first time miss with some other cache side channel protections. For example, we use SHARP, which was a secure replacement policy, and then we use Caesar, and we use Caesar S, which is a secure address set randomization approach. And we also implemented scatter cache, which is randomization approach, set partitioning, away partitioning, which are 2 commonly used partitioning approaches. And using this, we looked at the overall performance for a stress test, and a stress test is it's basically a spec benchmark, and one copy of the spec benchmark is running on each core. And since we have the same benchmark running on each core, we have a lot of shared code in the system. So we kind of artificially increasing the amount of shared code in the system. But yet we found that the overall performance of first time miss was very similar to the baseline. All these numbers are normalized to a baseline cache without any differences. So that indicates that even with a lot of shared code, the number of first time misses seem to be low. And overall, it looks like if you want a good trade-off between security and performance, first time miss plus sharp seems to be like a good approach or a good way to go, because the overhead is pretty low. In this particular case, it also looks like set partitioning is working pretty well, because we have the same benchmark running on each core, and in that case static uniform partitioning is actually pretty good, because all processes would have similar utilization. And then we also similarly did simulations for Parsec, and for Parsec we found that first time miss overhead was pretty low. It's important to note here that we used a version of first time miss in these simulations which only caused the first time miss penalty for read-only cache lines, and this, well, for cache lines from pages which are cache line addresses in pages which have a read-only permissions, and that's because if we allowed all cache line to have first time miss penalty, then we got like 5% or more degradation in performance, which is not desirable. And since side channel attacks typically tend to use code, and code is usually read only, like for example shared library code at least is usually read only, not all of it but most of the time. So we thought that this is a much better we felt that this is a good trade-off in terms of security and performance for us to have, because we don't want to give up too much performance for security, seeing as this is a low overhead approach. Okay, so moving on, we also had several other performance results for multi-programming scenario, but you can look at the paper if you want the details of those. But let's conclude now. So if you look at, we've introduced a new approach called first time miss to mitigate shared memory cache side channels, and we've proposed a low overhead implementation for the last level cache for these shared memory to implement this approach. And our evaluation using spec and parsec benchmarks indicates that the performance overhead is pretty low. So that makes it a nice performance security trade-off. Alright, so those are the key things I wanted to say today. Thank you for your time, and I look forward to your questions during the QA session.